Hello, everyone, and welcome to session 5 of DEM and CFD-DEM with PhasicFlow. Actually, this is the last session of this lecture series, and we are very glad that we spend this time with each other to learn new things. Today, we are going to talk about resolved CFD-DEM simulation, and we'll learn how we can perform two-phase and three-phase system simulation using PhasicFlow Plus. I am Hamidreza Norouzi, and with my friend and colleague Bahram, are going to present this lecture to you. Bahram, say hello, and please give us a brief overview of the topics that we covered in the previous session. Thank you.
Yeah, thanks a lot. Also, hello from my side. Welcome back, everybody. It's great to see you again. As Hamid already mentioned, we hope that you enjoyed this lecture series in the last couple of weeks, and hopefully you learn new stuff. I would also appreciate, like last lectures, if we do it in a quite interactive way. Please, if there are questions, if there are concerns, feel free to put them in the chat. So either I will read through them or Hamid will help me with reading them, and we try to answer and cover them as good as possible. So as Hamid already mentioned in this last session from this lecture series, we are going to focus on resolved CFD-DEM. So you already learned what is DEM, how DEM works, and how can you do your first DEM simulations with PhasicFlow as an open source DEM toolbox. And then in the last session, we already started with doing CFD-DEM, basically the coupling between fluid and particle flow. So because in most of the processes and phenomena which are happening around us, we are not dealing just with particles. Usually there's also some fluid involved. So therefore, this fluid particle interaction or this CFD-DEM approach is quite interesting and important. So for the CFD-DEM, for the DEM part, of course, we will use PhasicFlow, and for the CFD, we are relying on a very good and well-developed CFD package, open source CFD package called OpenFOAM. So for those of you who are already familiar for OpenFOAM, it's great. So you know how reliable and how good this package is. But for those of you who are not that familiar with OpenFOAM and you want to get more into this field, we have also some good news. From next week, we will start with our introduction to OpenFOAM lecture series. Please feel free to join them. Back to the topic. So the CFD-DEM that we are doing is basically for DEM, we are using PhasicFlow, and for CFD, we are using OpenFOAM. So, but just to make the things quite consistent and to remove the confusion, this package is called PhasicFlow Plus. So whenever you want to do CFD-DEM simulations, you need our PhasicFlow Plus package, which is basically a combination of PhasicFlow and OpenFOAM. How you can install it is something that we try to cover and explain in the last session. Please, you go and check it. You can check, of course, the already available videos, but you can also check the GitHub page of the PhasicFlow Plus, how to install it. Good. So with that one said, today we want to go for unresolved simulations. And let me share my screen.
Okay. Where can I find PhasicFlow Plus?
Basically, for thanks. That's a quite nice and good question. Let me open. Okay. Yeah, and this one. So if you search for PhasicFlow Plus and GitHub, that's most probably one of the first things which will pop up. So for me, it's of course the very first one based on my search history. For you, it might be somewhere among the first 2 or 3 ones, but I think as far as I know, it shows up quite on top. So, and yeah, just Google simply PhasicFlow Plus GitHub, and then you can go to this web page, and there are some explanation. Yeah, what is going to come, what is new, how can you install it, and some explanations. There's also another very important point. At the moment, at this minute that I'm talking, the release version is 0.1, but the version that we recommend to use, although it's under development, it's version 1. And this lecture series is also based on this version 1 version of PhasicFlow and PhasicFlow Plus. So please consider that one. If you install the 0.1, there might be, or some functionalities might not be available there. And we have the plan to release the version 1 in soon future. So don't worry, there will not be that many big changes in there when we are releasing it. Good. So let's have a look into the PhasicFlow Plus code and see what do we have there. So if I go to my PhasicFlow installation directory, basically after you have PhasicFlow and PhasicFlow Plus installed, you have two folders in there at least. One is basically PhasicFlow, which is responsible for DEM side, and the other one is called PhasicFlow coupling. In this PhasicFlow coupling, basically you can find the PhasicFlow Plus or the coupling between the CFD and DEM stuff. Going in there, we have our familiar structure. So there are a couple of files and folders, but among them, I would say the most interesting and important ones for you as the ones who wants to start in the field of CFD-DEM are these tutorials. And if you want to do developments, I would say solvers might also get interesting in the next step. So going into the tutorials folder, basically for each and every solver that we already developed, we try to provide at least one example tutorial or case setup. So far we looked into the unresolved sphere PF plus, and that's what we did in the last session. Basically, with that solver, you can do an unresolved CFD-DEM simulation. If you want to do a coarse grain simulation, then you need to use the unresolved grain PF plus. Basically, the setup is quite like the unresolved sphere PF plus. That's what we did last time. And for the coarse graining, you can go back to the 2 weeks ago session where Hamid explained how can you do coarse grain setup in PhasicFlow. It's exactly the same setting and setup also in here. That's the good thing. So if you learn PhasicFlow, basically you almost know halfway how to use PhasicFlow Plus. And for knowing the other halfway, you need to know OpenFOAM. So as simple as that.
And maybe I add something here that we provided 2 or 3 tutorials for each of these unresolved solvers.
Yeah, thank you very much. Yeah, if you go inside, you can see, for example, for this unresolved grain PF plus, we have this cylindrical fluidized bed, and we have also the normal rectangular fluidized bed. For some we have more, for some we have less, so but we are adding to them. So slowly as we are going through, whenever we come up with a new case setup with some new things that we think that they need extra explanation or they need extra sample case setups, we try to add them to our tutorials. Then if you look a bit closer, you see that we have 2 more folders which are starting with the word resolved. So we expect these ones to be our resolved solvers. The first one is called resolved sphere PF plus. So that's the equivalent to the unresolved sphere PF plus, but with the main difference that this one will do the resolved simulations for us. I repeat it once more. What's a resolved simulation? A resolved simulation means that the CFD mesh or grid is finer or smaller than the particle size. So basically, that means that the flow around the particle gets completely or to a very good extent resolved in this type of simulation. The advantage is that basically we are dealing with a quite detailed and physics-based simulation, physics-based DNS, direct numerical simulations of the particles. But the disadvantage is that since these type of simulations from the CFD side are quite expensive, we cannot afford too many particles in this simulation. So if you want to run, I don't know, a few 10, a few hundred, or even a few thousand, resolve might be the right selection for you. And the cool thing is that then you don't need to rely on any type of drag model, leaf model, or any type of these models. But if you want to simulate a system with hundreds, thousands, millions of particles, then there is no option except for going for the unresolved approach. In the unresolved approach, unlike the resolved, the particles should be much smaller than the computational grid size. So,
okay, may I ask a question here?
Yes, please.
How fine should the grid be for a resolved solver?
That's a very nice, but at the same time tricky question. Basically, the minimum, really, the absolute minimum number of cells is around 3 to 4 computational cells per particle. But what we can recommend is at least like between 5 to 10 cells that you can resolve a reasonable flow profile around the particle. If you are familiar with CFD, you know that's also a typical recommendation on the CFD side. When you want to resolve a flow profile, you need really absolute minimum of 3 cells, which I would say nobody is using that, but a reasonable minimum of 5 to 10 cells per diameter are required. Also on pure CFD, and the same thing is also valid here. So however you have more cells, the simulations will get more accurate. But yeah, again, the drawback is that computationally you cannot afford it. On the unresolved, on the other way around, basically we need to have at least two, or better to say, 3 particles per cell, per computational cell. This is the minimum, but there are some nice means and ways to go around this limitation and go even up to dimensions like 1 particle per cell. That's something which is outside the scope of this lecture, but just be aware that there are also possibilities which are also partially built into the PhasicFlow, which enables you to do unresolved simulations with particles close to the same cell size as the fluid grid. Good, Hamid. Before I jump to the next point, are there any questions, or do you want to add something?
No.
Good. Thank you very much. So the next point is that there is also a second solver here. And if you compare it with the first one, you see there is a VOF in the name. That's standing for volume of fluid. For those of you who are familiar with CFD, you know that's an approach for resolving multi-phase flows with sharpening the interface. So as you could already guess, this first solver is used for single fluid CFD-DEM simulations, and the second one can be used for multi-phase. So one phase is solid, and we can have also 2 or a couple of fluid phases. As far as I remember, at the moment we have just for 2 fluid phases, but on the longer run, it will be also extended to multi-phase fluid phases. Good. The main focus for today will be on the resolved sphere PF+, but we will also have a short look into the VOF version of it also. Going there, as already mentioned, there are a couple of examples provided, and we also try usually to name them in a way that the names are quite clear, or as clear as possible, explaining what is happening in these tutorials. So the first one is called damping rotation. Basically, that's a single sphere which is rotating in some fluid medium, and because of the friction of the fluid on this sphere, it slows down. The second one is called floating balls. That's a group of balls which are getting floated in some fluid medium by the fluid which is coming from the bottom. The third one is called floating ball dynamic mesh, or DY mesh. Basically, this is the same setup as the previous one, except that in here we also have the dynamic mesh, which is responsible for refining the CFD grid wherever it's required. That's the case that we are going through today, so don't worry, you will see how does it work. And
Okay,
then
I have a question here. First, why do we use dynamic mesh? And the second that is coming from the chat is 5 to 10 cells in each direction per particle, or for the volume of the particle?
Okay, great. Thank you very much. So regarding your first question, basically, yeah, we always want to have the cheapest, but at the same time, the most accurate simulations. So to make a CFD simulation cheap, what's the solution? Is to have a coarse grid, a coarse mesh in there. But we know that comes at the cost of accuracy. How can we compensate for that? Basically, then we can resolve the mesh at the locations that we need it. For example, if there is an interface, then we can just resolve the mesh on this interface, if this interface is the most important thing that we want to capture. Everywhere else, the mesh is coarse, and just on this interface, the mesh is fine. But we know in a multi-phase flow, this interface is not a constant thing, so it's moving during the time. Therefore, we use this dynamic mesh. Basically, the dynamic mesh tries to detect this interface, and from based on the location of the interface, it tries to refine and unrefine the mesh in these locations. We will see how this can be set up and how does it work. And now back to the second question. Basically, it's in each and every direction. So that means that if we consider 3 cells, so and in 3-dimensional, we are talking about 27 computational cells per particle.
Okay,
But
and
again, that's the absolute minimum that I strongly recommend to avoid it. Go for above 5. So above 5, I would say 10 is a sort of a sweet spot. Yes, please.
what do you mean by interface? Is it the particle surface or something else in
By
the
the
solid?
yeah, that can be also defined by you. So it can be either the particle surface, the surface between the solid phase, which is the particle and the fluid, or the surface between the two fluids. For example, if we have the air, water, and particles in there, so this is the interface. This is the interface between can be the interface between the air, water, between the air particle, between particle, water, and all combinations are possible. The thing is that, as far as I'm aware, in the stock OpenFOAM, because this is a limitation or this is the setup which comes from OpenFOAM, you can have just one of them resolved at the time. So you cannot resolve all of them at the same time. There are some extra developments and some additions, add-ons that you can add to OpenFOAM, which also enable multi-field resolving. But let's discuss it when we are in the file, because then I think it will get more clear how you do the setup. So the last example that we have in here, it's basically a mixer with a bunch of particles and some fluid inside, which tries to mix these particles in this fluid. As I said, as I already mentioned, the floating balls with dynamic mesh is the case that we want to use for today. But before going there, Hamid, are there any other questions or points from your side?
I just wanted to ask if it is possible to add those extensions to the current file, to current code, to somehow enable this double refinement mechanism in PhasicFlow.
Yeah, that's a very that's a very nice question, because that brings me to the point. So if you want to add some functionality to the PhasicFlow or to OpenFOAM, basically you can easily do it. So they are not that much interdependent, although they are working very nicely synchronized together. But if, for example, if you want to add this library, that's an OpenFOAM library. You just compile it for your OpenFOAM version. If you manage it, which you hopefully will, then it's there, and then you can just simply import it in this simulation and it will work. So it's as easy as that. And that's one of the very, very big things that we are proud of. So basically, you don't need to care about PhasicFlow at all. If you are familiar how to add a new model into your CFD side of the story, then add it. It will be in the PhasicFlow Plus automatically. And the other way also, if you add a model into the DEM side, into the PhasicFlow, it will be available in the PhasicFlow Plus automatically.
Okay, thank you. Thank you very much.
You're welcome. Okay, good. Let's copy this to our working directory. So let me first go to my working directory, which is my desktop. I already have this one copied here because, as you might have already learned from the previous lectures, running these cases take a bit time, which usually runs out of the time frame that, or the time schedule that we have for this lecture. So therefore, I usually start these cases before the lecture, that we have the results by the end of the lecture. So let's create a new folder and call it, lecture 5. Going back and copying this one from here to the lecture 5. Good. The case is copied. We are ready to go. Let's see what do we have inside. As we learned last time, so I try to repeat some things a little, because last time we had to rush through some stuff. This time we try to clarify them a little more. There are a few folders, basically. We have a couple of folders. Part of them belongs to PhasicFlow, to DEM. Part of them belongs to the CFD, OpenFOAM. And there is one file which is basically doing the magic, which is the setup file, and is doing the synchronization between the CFD and DEM, which I will show it to you. We have seen it already last time. It's called coupling properties, which is sitting constant, but we will see it also in detail. Good. So basically, I hope that you already got nicely familiar with the PhasicFlow. And if that's the case, which hopefully is the case, you know the case setup and settings are the two folders which belongs to the PhasicFlow. So basically, we should be able to find all the relevant settings for the DEM simulations in these two folders. Let's through it and let's go through them and see if that's the case. So for that one, of course, I need a text editor. Good. Starting with the case setup. There are 3 files in here. We don't need this one. I think this is a leftover that we need to clean it up before we release the version. So we have the 2 files which are called interaction and the shapes. Guessing from the names, basically in the interaction, we set up the properties and the way that the particles are interacting with each other and with the other material or with the other solids like the walls. And in the shapes, basically we define the shapes of particles. Just a disclaimer, for the moment, we are just covering or supporting spherical particles, but with the shapes, you can define a mixture of spherical particles with different sizes. Hopefully, in soon future, the non-spherical particles will be also added to the PhasicFlow and consequently to PhasicFlow Plus. Another good news is that the code has been written in a way which are quite generic. So again, if we just add the non-spherical particles to the PhasicFlow, they can be both reasonably easily used also on the PhasicFlow Plus. So with that, I want to say, if you're also willing to contribute to the PhasicFlow or PhasicFlow Plus, you are very welcome, and every contribution is highly appreciated. Good. Interaction file. So the very familiar header that basically you don't need to worry that much. Then we define the materials that we have in there. We have we define 2 types of materials. One is the sphere material, and the other one is wall material. And then for each material, we also define their density. So for the sphere, we take a density of 1,000, and for the wall, we take a density of 2,500. Regarding the units, like OpenFOAM, all the units in PhasicFlow and of course PhasicFlow Plus are SI units. So please avoid any non-SI unit. So basically, if it's written density at 1,000, even if this comment is not here, the density by default, or the unit by default, is kilogram per square meters. Per cubic meter. Sorry, per cubic meters. Yeah, that happens once in a while. Good. Then basically the contact list type is sorted contact list. Leave it as it is. Hamid did a great job by explaining that. And also the model coefficients. So the coefficients that we need for the interaction between the particles. Again, Hamid went through them in reasonable detail. The point is that if you want to go into these coefficients in full detail, that will be all on its own lectures and not just a lecture. And what I also need to I don't want to call it warn you, but make you aware of, is that these coefficients also play a quite important role, because by setting them, you are defining how these particles are behaving against each other, how they are repelling each other, how they are sliding next to each other, how they are rotating. So therefore, that's also quite important thing. But the bad news is that these coefficients are not that easy also to measure. But that's a different topic. When we start with the DM, we consider that we have this information already. And of course, our contact search, so how the contact between the particles and walls should be searched, and the different settings in there, which again Hamid explained it very nicely in the last sessions. So Hamid, are there any questions, or is there any point that you want to add to this part?
Yes, about the interaction part. Let's just scroll up the model. Yes, the model dictionary. Why do we provide 3 numbers for each parameter, for example, Y, EAFF, or GEF, EFF, or the others?
Thanks. That's a very good question. So I think you are the right guy to answer this question, but I try to answer it from my perspective, because we have 2 materials, and that's why we get more of these coefficients. So if you have just a single material, you need 1. But since we have multiple materials, so we have more of them. But about the structure and the sequence of them, maybe you can explain it, because you are much better expert than me.
Okay, thank you. For example, consider the first one. We are providing 3 numbers. The first is the interaction parameter between material 1 and material 1. The second is between material 1 and material 2. The third, which is empty here, is again between material 1 and material 2, and that's why we just skipped that one. And the last one, which is the third one here, is between material 2 and material 2. So somehow it is a square matrix, but we are providing the upper triangular part of the matrix, because the lower triangular is similar to the upper triangular, and somehow we thought that, okay, why don't we just provide the upper triangular part, not the whole matrix? That's why you see a kind of upper triangular matrix here.
Yeah, great. Thank you very much. So it's always the question, how can you put the things together and how can you visualize it? This is the way that we thought might make the most sense. But yeah, but again, PhasicFlow and OpenFOAM, they are both sitting on top of C++. PhasicFlow and OpenFOAM, they're both sitting on top of C++. So basically, you can also bring this line up here, and that should not change anything. So you can structure it as you wish, as far as you know what does each and every setting and parameter means. Good. Going to the next file, basically in here, we are defining the shapes. So so in here we are having just a single size or type of sphere. So, and we call it sphere 1 with a diameter of 3 centimeters. Again, units are SI. So this is 3 centimeter. And for them, we use the sphere material. So the material that we define for sphere is assigned to these spheres in here. Good. So that was interaction and shapes. Let's go to the next one, settings. Basically in the settings, we continue with setting up our DEM simulation or the DEM side of the simulation. Another cool thing is that, so what you can do, you can also combine DEM and CFD-DEM or DEM, CFD, and CFD-DEM. How? For example, for setting up a case, that's what we will also do today. We can first do a DEM simulation to drop a few particles into this box without any airflow or any fluid flow from bottom. And as soon as the particles are at the bottom, then we started blowing the water or pushing the water or blowing air from the bottom. So therefore, then from a DEM simulation, we switch to a CFD-DEM simulation. And again, later on, we can go, for example, to a pure CFD simulation, which we are not going to do today. Good. Hamid, do you want to add anything to this part?
No, I think everything is clear.
Good, great. Thank you very much.
And here I see some leftovers, neighbor list, update interval. These are the automatic and default. These values have automatic and default values in the new version. So you don't need to provide them.
Yes, thank you. That's also a very good point. The first point, we define the global box where our simulation is sitting. So, and if a particle goes beyond this box, what happens to it? So these are the minimum and maximum coordinates of this box. And these are the boundaries which are getting defined on this box and what also happens to the particle. So in here, we have exit for everything. That means that if a particle hits this wall or this boundary, it gets removed from the simulation by setting it to exit. But of course, you have the option to make it reflective or periodic or whatever, or something like this. Good. And the next step, basically, we define the geometry or DEM domain geometry. We already learned there are a couple of nice ways that you can create your geometry. So one way is, of course, using the built-in functionalities of the PhasicFlow for creating your DEM geometry. So for example, in here, we are going to create a cube. So therefore, the type is a cuboid wall. We define the center and the edge length in all 3 dimensions and how many divisions should it have in each and every direction. Also, what type of material is it? And if the walls or if these walls are moving, which is not the case in this scenario. That's one option. The other option is that I find it very nice. You can import it from an STL. So if you have an STL file, you can also import the geometry from an STL to your simulation, which is quite useful if you have a very complicated or rather complicated case. For example, you might already remember we have this conveyor, this screw conveyor. That's a quite complicated geometry that you cannot generate it that easily with such simple functionalities. Therefore, you just simply make an STL file, a surface file in a CAD program like FreeCAD, CATIA, Saloom, or whatever, and then just import it in here. And there is also a third one, which is the most relevant for the CFD-DEM or for PhasicFlow Plus. Basically, you can import the geometry from the CFD side to the DEM. So we have some examples. If you check through other examples, you will see them that you can import the boundaries of a CFD simulation as the walls or as the surfaces to the DEM side. And that gives you a very nice transition between CFD and DEM on the geometry side. Good. And then comes the particles. So basically with the particles, we do assign them an initial value for the velocities, for the rotational velocities, and also the shape that they have, and also the selectors, which is not the case in here, because in here we are going to locate the particles inside the geometry from the very beginning. So for that, we do the positioning of the particles. We position them randomly. And how many particles? 20. As I said, since we are dealing with a resolved simulation or resolved CFD-DEM simulation, usually we are dealing with rather small number of particles, a few 10, a few hundred, or maximum a few thousand particles. Because again, consider if you have, I don't know, like a 1,000 cells per particle, and if you have 1,000 particles, then you're already talking about a million cell CFD mesh, at least. Then we are positioning them with a distance of 3.5 centimeters, just to make sure that the particles are not overlapping with each other. So this minimum distance should be the particle diameter, because if it's smaller, that means that it might be that you're pushing two particles into each other. And as soon as you start the simulation, it starts calculating the forces, and then it will shoot the particles out. So be careful with that one. And then it position them with like 200 iterations. Okay, where is it going to position them? We just want to position them in a box in our geometry, of course, and these are the minimum and maximum of this box that these particles are going to be positioned. And yeah, how many are the maximum number of particles? Basically, it's somehow consistent with the number of particles that we want to have, and if we want to do any sorting on them, which we don't really want in this case. Good. We define our geometry. Yes, please.
Let me just add some point here about the positioning into the box or any other region type, for example, cylinder, sphere. It locates the center of the particles, not the whole particles. So you should somehow consider a smaller box, a box that is smaller than the actual geometry of the simulation, so you don't have any particles that are in initial contact with the physical walls in your simulation. Just consider this when you're setting up the box or any other regions in your simulation for positioning, for initial positioning of the particles.
Thank you very much. That's a very nice and valuable point. So please don't forget it. It's about the central particles. And as Hamid said, if you do this mistake again, it might be that you're pushing the particle into the wall, and as soon as you start the simulation, it will be shooted somewhere and cause some instabilities in the simulation, even diverging. Good. And then so far we created the geometry for our DEM side. We created the particles for our DEM side, and let's see what settings do we want to have. So basically, yeah, this is the name of the simulation. This is the coupling utilities. This is the library that we are importing, which we don't need for the first part of simulation, which is a pure DEM simulation, but we will need it for the second part of simulation, that we are going to do a CFD simulation, CFD-DEM simulation. The first part is a DEM simulation because we just want to position some particles and drop them to the bottom. And then in the second part, we want to float them with some fluid from bottom. So this is the delta T for the DEM part of the story. Also in the CFD-DEM coupling, the same delta T will be used. The start time, end time, save interval, and time precision for the DEM part are taken from this dictionary, but for the CFD-DEM coupling, they are basically taken from the control dict of the open form side of the story. So just be careful if you're doing CFD-DEM simulations, the start time, end time, save interval, and time precision are read from the control dict from there. And the reason is that because we want these to be synchronized together. And delta T, no, they have, since in the DEM and in CFD we are dealing with different delta T's, they have, each of them has its own individual delta T, and usually the DEM delta T is much smaller, so in like one order of magnitude smaller than the CFD, but it's not a prescription for each and every case, just as a rough starting point. So then we also define the gravitational point. Be careful, this is the gravitational point for the DEM, for the solid particles. This we won't affect on the CFD side. And then we also define the domain, basically the minimum and maximum or domain, and the rest of the settings are not that that was critical for what we want to do today, because Hamid went through them and explained them quite nicely last times.
Okay,
Good.
and let's just add something. This is the tutorial from the previous version, and in the previous version we had domain in the settings, but later we changed it and created another dictionary for the domain that you see under settings folder, domain dict. So we don't need that domain here.
Yes, so that have been moved here. So
yes.
Thank you very much, Hamid. So it seems that we have some cleaning work to do, but the thing is that if you have it at two places, it does not really harm. So it just don't use what it does not need. But if you don't have it at the right place, then it will complain to you. Good. So that was the case setup for the DEM. Now let's go to the CFD side. For the CFD side, for those of you who are familiar with OpenFOAM, you know we usually have three folders. One is the hosting the initial and boundary conditions, which is usually 0 or any other number. Then we have a constant folder, which we have the constants like the viscosity models, like turbulence model, mesh, and such stuff are stored here. And then we have the system, which the settings, the numerical settings, and everything is happening in there. We don't have the 0 folder or this initial and boundary condition folder yet, and you will see why. The reason is that, as I said, we want to run the DEM for, I think in this case, for 2 seconds. And after 2 seconds, we start with the CFD. So what we will do, we will start the simulation just using pure DEM up to 2 seconds. And then we will copy these initial and boundary conditions from this fluid field to this time 2, and then continue from there with the coupling. So let's look into the constant. Looking into constant, there are a couple of files in here. And the first one is basically what I already mentioned, is responsible for handling the coupling settings between CFD and DEM. The only thing, or the main thing, is that in here we have a sub-dictionary which is called resolve, since in this case we are dealing with a resolve simulation, and there are a few settings in there. The first setting is that what we do when we are doing this coupling, basically we convert DEM particles, which on the DEM they are a point plus a radius. If I'm not wrong, Hamid, please correct me if I am. We convert them to a surface, to an STL surface on the CFD, that we can do quite accurate calculations in there. So, yes. And with this, is that true?
Yes, that's right.
Okay. Then on the CFD, we convert them to STL, and this defines the resolution of this STL. So however you make this number bigger, that means that you have a finer surface, so consequently a more smooth surface, but as a result, higher computational effort, because more surfaces or forces on more surfaces needs to be calculated. So I recommend to go for a decent value, I don't know, around 20, 30, and that should do the job. So for most of the cases, if you have a single sphere, go for a few spheres, go for a higher number. But if you have, I don't know, a few thousand, a few 10,000, you can stick to, like, I don't know, something between 10 and 20.
Okay, I have a very interesting thing here is that when we compare the coupling properties dictionary between the resolved and unresolved, can you compare those two to see the differences and see what we need to provide in each case?
Yeah, just a second. I need to so I need to find it first. It will be here in a second. And as that constant coupling properties. Let me put it down. Ah, come on. When I don't want it down here, it always suggests me to add it down here, and when I want it, it says resist. Yeah. The thing is that I think, Hamid, that was a very good idea that to put these two side by side. If you look into the unresolved, we have so many settings. So there are many more settings. And the reason is that because in unresolved, we are relying quite a lot on the models. And these are the models which are handling or which are taking care of different type of calculations, like the porosity, like the drag calculations. But in the resolve, since everything is getting physically calculated, is getting calculated out of the resolved shapes, we don't need these models. Hamid, do you want to add something here?
No, just I just wanted to mention this, that okay, in the unresolved solver we need to provide the unresolved dictionary which contains so many settings related to the drag force calculation, porosity, and mapping of the particles of the particle properties onto cells. But with the resolve solver, to be honest, even these settings were not necessary, and we could use some default settings. But as you see, we are providing nothing here because everything is resolved around the particle, and the interaction within the particle and fluid is calculated during the simulation.
Yeah, thank you very much. And that's one of the very nice examples that shows the value of a resolved simulation. So basically, everything is handled sort of automatically using the physical formulation, which is on the background, and you're not relying on the models. But as soon as you go to the unresolved, although it has definitely its own advantages, but you have to be very careful with the models that you're selecting. And if you're selecting the wrong model or the wrong settings for models, then it will end up in a wrong simulation. For those of you who are familiar with approaches like runs in turbulence modeling and DNS. So in DNS, we don't use any model. Its computation is super expensive, but we don't use any model. So whatever comes out is correct and accurate. But in runs, on the other hand, it's very cheap in computation. But yeah, if you do a slight mistake in the setup, then the results are not reliable anymore. So this is not a perfect one-to-one comparison between this one and that one, but I think they're quite close. So also in this sense.
Yes.
So in the first one, basically in here, you set the resolution of this sphere. So that means that if you go for a higher number, you get more resolved sphere. And however, it's more resolved, that means that it's closer to reality. But again, that's a trade-off that you need to go through. And in the next part, we can select if we want to save the ID of the particles on the CFD mesh as a field or not. In this case, we don't want to do it, but that we have an option. It's a quite nice thing for post-processing. So if you want to see the history of a particles on the CFD side, if you save this ID, then you will see how it's moving around in the field. And the last one is the saving the STL. That means that whenever it's doing the calculation, it also keeps the STLs that it did the calculation on them. So it's a cool thing for the visualization in the latest step if you want it. Yeah, so let me close this so that I get the full picture. And yeah, the particle mapping, the typical story, and it's not really that relevant for this lecture. Then comes, let me keep the dynamic mesh to the last. Let's go for here. In the transport properties, basically we define the material properties for the fluid medium. In here we are telling the solver, the CFD solver, that we are dealing with a Newtonian fluid with a kinematic viscosity of 1.5 times 10 to the power minus 5 and a density of 980. So that's something close to water, just for your information. And for turbulence, for this simulation, basically we are relying on a laminar approach. So honestly speaking, we did not really calculate if it's turbulent or laminar, but for a case setup or for a demonstration case to show the functionality and capabilities of the development, that should be good enough. Good. Then comes this next one, dynamic mesh dict. So if you remember, we had a dy in the next in the naming of the example. So floating balls dy mesh, and that's where this dy dynamic mesh is coming from. I already explained it, Hamid. Thanks to Hamid also for contributing and clarifying it. So basically, with the dynamic mesh, what do? We have the CFD background mesh, or we have the CFD grid. And then based on the field, for example, based on the pressure field, temperature field, phase fraction field, or whatever field that we have, we make a decision. At some points, we try to refine it. So how do we do it? The first thing is that, of course, yeah, we use the dynamic refine finite volume mesh. So this is the library which is responsible for this type of refinement. Keep it as it is. Then the next setting is that how often do you want to refine and unrefined, because again, this is computationally expensive, that takes you time. So if you have something or some simulation that the change in the property that you're tracking for dynamic meshing is not fast, go for a bigger number. So if you go for 10, after each and every 10th CFD iteration or CFD time step, it does this refinement. If you go for one like this one, after each and every time step, it does it. So, but if you have a quite dynamic environment, so for example, if your interface is moving quite fast and in each time step, you expect it to change. So therefore, go for a smaller number, or in the in the finest way, go for a value 1. Then now we decide which field do we want to refine. So in here, we decided for the field void fraction. Basically, void fraction is defining the void fraction of the solid in the fluid phase. So therefore, you see, therefore, in here, we are resolving the boundary between the solid particle and the fluid. Good. In here, it's an easy decision. Why? Because we don't have any second fluid. So we can simply go for this one. But if you have a second fluid, then it gets a bit tough. Should you go for refinement of the two fluid interface or the fluid and particle interface? Then you define a minimum or lower and upper refinement level. That means that, okay, if the value of this void fraction is less than 0.01, do nothing. If it's above 0.09 or 99, oh, sorry, it does not mean do nothing. It means that unrefined to the original mesh. So if you already refined the mesh in a location and the value of the void fraction goes below or above this value, so if it goes below 0.01 or it goes above 0.99, then it tries to unrefine the mesh. But if the value of the void fraction is dropping in between these two values, then it tries to refine in this cell. So if in a computational cell, the value of void fraction is 0.5, then it tries to refine it based on the settings that you have in the following. So this unrefined level is basically the maximum number of cells that it keeps unrefined before it goes to the next step. This is just a sort of relaxation setting for the refinement algorithm. And then the number of buffer layers, that means that when it refines the cell, how many cells outside should it further refine before it goes to the coarse mesh? So yeah, 1 is quite an okay number, I would say. If you want your refinement to diffuse deeper into the mesh, go for a bigger number. If you want to stay that it stays close to the surface, go for value as small as possible, like 1. And then comes the next point, which is the maximum refinement. So how many levels of refinement do you want to have on your mesh? So in here, it goes for a maximum of 2 levels. That means that in each and every direction, it cuts the cell in maximum 4 cells or 4 portions. This is something which goes into the open form field. And if you want to know more about it, of course, I will show it to you a little more when we are post-processing the results. But if you want to know more, please feel free to join our next lecture series. And in there, when we are talking about meshing, and especially snappy X mesh, that will be one of the things that we are going to cover in detail. Then we have the next point, which is maximum cells. So that means that it starts refining. So let's consider that your original mesh is 100,000 cells, and it starts refining. If it reaches 200,000 cells, that's the value that we have here, it does not refine the cells further, even if the value is falling in between these two, because it already reached. The reason for that one is that, yeah, with this, you can control that your mesh does not get too fine and your computations does not get too expensive. And yeah, basically with changing a mesh, sometimes you also need to recalculate and correct the fluxes, which is not the case here. And it also asks you if you want to write these refinement levels into a field that you can visualize it in your ParaView, which we said yes, but I don't see any need for it. Good. Okay. I mean, before I go to the next folder, is there anything that you want to add?
I have a question from the chat. Is it possible to simulate or be similar to a sediment transport model, like entering the CV or coefficient of Bingham plastic formula as an example?
So basically, you're talking about you're talking about a non-Newtonian fluid. If I'm right, am I right? I mean that was the question. Yeah,
that's what I think about the question.
Thank you. Thanks for confirming. If we go back here again, that's also one of the very cool and magical things. Although this PhasicFlow Plus is putting PhasicFlow and OpenFOAM next to each other in a quite seamless way. So you see, if I also open one of the setting files of the PhasicFlow, they have quite a similar setup style. Although they're quite similar, but you can modify each side sort of, rather independently, as far as you are sticking to the physics. So make this one the bold part. Stick to the physics. Don't suit something that is not in reality. So if this viscosity model that you're going to use does not exist or does not make sense, then most probably you'll face problems. But if that's a real thing and that can work in reality, then you can simply come to the CFD side. Instead of Newtonian, you go for a non-Newtonian, and then you select the type of model that you have. You can, again, as far as I know, OpenFOAM supports many different type of non-Newtonian fluids. But even if it's not there, you have the possibility to program it into OpenFOAM. So for that one, you can visit our other lecture series, which is about programming in OpenFOAM.
Yes, and we already covered that one. I think we in the first session.
Yes, I think so yeah, we try to explain lots of things. Good.
And let me just add one point here. With the resolve solver, I think it is already there, and you just need to change the viscosity model in the OpenFOAM side, because the solver solves resolve the fluid flow around the particles. So with the non-Newtonian fluid, you can also calculate the shear stress on the interface between the fluid and particle. And I think that physically it is correct to use it. But with the unresolved solver, since we are calculating the interaction between the particles based on the assumption that the fluid is Newtonian, I think there should be some modification in the coupling part. And maybe these changes are somehow unphysical in the unresolved solver.
Okay, thanks for adding that. So I wasn't really aware that the drag model and the models that we have in there are Newtonian ones. But if that's the case, then that definitely should be considered. But if the drag model that we are using can support also non-Newtonian, then basically what we deliver from the CFD side to the DEM is a simple viscosity. So and that can come also from a non-Newtonian fluid. Mm-hmm. So, no limitation from CFD side. On the unresolved, on the resolved one, that's also no problem. But on the unresolved, as Hamid already mentioned, please be careful with the type of models which are used, that they are compatible with the physics that we have at this side. Again, it's this. We go back to this bold title. The physics should work. So if, for example, the drag model that you're using is for a Newtonian, and you force it with a non-Newtonian fluid, then it might work. But in the best case, it might work, but the results are physically wrong. And in the worst case, it will just crash. I'm not sure which one is really the worst case, because I prefer that it crashes rather than giving
the best case. The best case
is
crashing, I think.
Yeah, because if it gives you false physical results, sometimes it's quite a challenge to find the source and the problem. Good. So let me close these ones and go to the system. So in the system, we have a couple of other files. The first one is called BlockMeshGig. BlockMesh is basically responsible, or we use the BlockMesh utility for creating our CFD grid. So we generate our grid using BlockMesh. There are many tools and softwares out there, but for this simple cube, I would say this BlockMesh is a quite nice tool to be used. So, and it has, or it should have, the same dimension as the cube that we have on the DEM side. We have to take care and be careful about that. If we are not importing the geometry, if we have been importing from the CFD side, it would have happened automatically. But in this case, since you're generating them separately, you have to take care of that. And this is also the resolution. So we have 20 cells in the X, 20 cells in the Z, and 90 cells in the Y direction. As simple as that. So as you can see, that's a rather coarse mesh, but we will see it in the post-processing. Then comes the control dig. Basically, that's the place that we do the time settings for the OpenFOAM solver, and in this case for OpenFOAM and PhasicFlow Plus, or better to say for PhasicFlow Plus solver. So the setting is from start time, and you can see we set the start time to 2, because as I said, from between time 0 and 2, we will run a DEM simulation, and from time 2, we will start the CFD-DEM simulation. So in the first 2 seconds, we settle the particles, and after the second 2, we try to float them. And the simulation will run for 6 seconds with a delta T of 10 to the power minus 3. As you can see, the delta T is much bigger than on the DEM side, but you don't need to be worried about that. Just set the correct delta T for the CFD and DEM side, and they will sync each other automatically. So these internal loops will happen, everything automatically. You don't need to worry about that. And Also, write interval is getting read from here onwards. So basically, it saves every 0.2 seconds. Then we have the decomposed parting. So basically, when we are talking about resolved CFD-DEM, then DM, we're talking about a few 10, a few hundred, or a few thousand particles. So it's computationally quite cheap. You can run it on a single CPU core. You don't need to do any effort on that. But then the effort goes mostly on the CFD side, unlike an unresolved. In an unresolved simulation, usually we have many particles. That means that the DEM is computationally very expensive and the CFD is rather cheap. So in this case, it's the other way around. So DEM is cheap, CFD is expensive. So what's the solution is the parallelization also on the CFD side. But basically, this parallelization also works on the unresolved case. You can apply it to all of them. What we do here, we try to break our geometry into 4 subdomains and do a parallel MPI calculations on that. For the PhasicFlow Plus, the CFD is always parallelized using MPI approach. But for the DEM, depending on type of PhasicFlow compilation that you have, the parallelization will happen. If you have a serial compilation, the DEM will run in serial. If you have an OpenMP, then it will run OpenMP on the CPU. And if you have a CUDA compilation, it will run parallel on your GPU card. So depending on what you have at the other side, it is like that one. But on the CFD, it's either serial or MPI. So these are the 2 options which are available at the moment. Good. Then FD schemes, basically in the FD schemes, you are setting up the CFD schemes. So for doing the time derivatives, the gradient schemes, the divergence, Laplacian, so forth, and so on. If you want to know more details about them, visit us in the next lectures, which will start from next week. And the same story is also valid for the FD solution. So in the FD solution, we define the solvers for each and every property and field. For example, for pressure, we are using this GMG. For velocity and turbulence things, we are using smooth solver and so forth and so on. And then we also need another solver for the immersed boundary divergence, because the approach and method that we have built in the current version of the resolved solver is an immersed boundary, is a volume penalty immersed boundary approach. And this is for calculation of this divergence field, which gets transported in there. Good, and then the typical pressure velocity coupling is happening done using Pimple, and since we have a number of auto corrections set to 1, that means that basically it's working like a piezo. Again, to know more about that, feel free to stop by next week. Good, I think I'm through with the setup. There is still one more, and that's the fluid field, but I will come back to it after I check with Hamid if there are any questions.
No, we don't have any questions, but I think that it's better to start the simulation, and during the simulation, you can explain the fluid field.
That's also an option. Let's follow Hamid's recommendation. What I can tell you, since I have the PhasicFlow on the GPU of my computer, and that's a quite good GPU, so I can tell you, it runs quite fast. I will see. Just give me a second. So let me change the font before I get some complaints from the colleagues. Good. Hamid, do you see it bold and clear?
Yes, it's much better.
Good. Okay, so as I said, for the first part, we need to run the DEM simulation. This, again, that's what I also mentioned in the past, this all run can be a very good hint on what steps do you really need to run for each and every simulation. The first step that we have in here is block mesh, which is for the CFD. You can also postpone it after the DEM simulation. It does not really cause any trouble at this stage, especially since we are not importing the geometry from the CFD side. If we would have been importing the geometry from the CFD to the DEM side, then you should have run the block mesh first. So the sequence of the comments should be logical. So let's start with the particles PhasicFlow. With this one, basically, we position the particles, these 20 particles randomly. Then with the next command, which is geometry PhasicFlow, we are creating our cube using the setting that we have. And now we can run the DEM simulation. And you see it. I said, I'm proud of this thing. So you see, it runs quite fast. We are running it for 2 seconds. But maybe I can use a few seconds from this time to explain to you about this fluid field. Basically, these fluid fields are the fields that we need for the coupling and for the CFD. And as I said, since we are going to start or continue the coupling or the CFD-DEM simulation from time 2, they should be copied as soon as the DM simulation is done. They should be copied to the time 2 folder, because from there the CFD-DEM simulation will start. Let's have a look in here and see what do we have. Basically, the first file is the immerse boundary divergence file, and yeah, for that one, basically simply set the what's the name, internal field and the patch boundaries to 0, and for the walls and the rest of the stuff to 0 gradient. This is something which will calculate automatically in the solver. It's just a dummy file that it needs for the solver to start. Then, if we go to the pressure, typical CFD setup, at the inlet we have a 0 gradient for the pressure, so the internal field is 0, and that means that we have a 0 pressure, initial pressure everywhere. This is a relative pressure. Then at the outlet we have a fixed value. That means that we are fixing the pressure at the outlet to the value 0, and on the walls is also 0 gradient. Quite typical and yeah, nice CFD boundary condition. And the same also applies for the velocity. If you look into velocity, we have a velocity field of 0 everywhere in the field at the beginning. Then for the walls, we apply a no-slip boundary condition. At the inlet, we have a fixed value for the velocity of 0.7 meter per second. Units are SI, please pay attention. And at the outlet, we apply a 0 gradient or a fully developed boundary condition. And the last file is the void fraction, which is basically the void fraction of the solid on the fluid side. And we set a value of 1 everywhere. At the inlet, it's also 1, and the rest is 0 gradient. And you don't need to worry, because this is also a field which gets calculated and filled automatically as soon as the solver starts. Good. So let me copy them, because I know that we need them, and go back to our solver. You see, our solver is, our DM part is already finished up to time 2. And if I go there, all the files and fields for the DM is already available there. So let me add also the files that we need for the CFD and the coupling part. And with that one said, we can start the CFD. But before that, of course, I need to create the CFD mesh. The CFD mesh is done. And then I also want to run it in parallel mode. So I need to decompose it. So I use 4 processor cores and then simply run the solver. So you can see it's really like running an OpenFOAM solver in parallel. So MPI run minus MP, so number of processors. We are using 4 processors, and the solver name is resolved sphere PF plus and minus parallels. So, and it starts. Good. I have done it already, so we don't really need to be worried about that one. And oops. Where is my second terminal? It's here. Okay, let me go to the bottom. Yeah, the simulation is already done. And then we need to, let me just move to the other folder. So the simulation is already done. And since I did it in parallel, so the CFD field, and coupling fields are written in the processor folder. Let's look at them here. Desktop, dynamic mesh. So the DM files are written in these time directories, and the CFD and coupling files are written in these processor directories. So if I go here, for example, to time 2.1, we have the coupling. So you see IB dive, volume fraction, and UP phi, and the rest of the files which are relevant for CFD. And then we need to reconstruct the simulation to visualize it. So for reconstruct, if you're going to reconstruct it, you have to reconstruct per mesh first, because we have a dynamic mesh, so the mesh has been changed. And then we have to do a reconstruct part for the fields. I think this one takes also some time, if I'm not wrong. Yes. So therefore, I don't reconstruct it, and we just simply jump into the post-processing. So I use the foam.foam because I'm not going to convert it to VTK. But for the PhasicFlow, let's convert it to VTK. We can convert just the coupling part, but I will convert the whole thing. That we can see it. We can see also the DEM part of the story. So Hamid, are there any points that you want to add before I start post-processing?
Oh, just again, when you're going to visualize the results of the DEM and CFD side by side, it is better to load foam.foam for the CFD part and load those .series files in the DEM part. Then they will be synchronized.
Great, thank you very much. That's also a very good and valid point. So let's load the results and let's start with the DEM results. And particles on surface. Okay, apply. And for the surface, I make it a bit opaque that you can see through it. And for particles, so let's make life out of them. Sphere. What was the size of the particles? How many do you remember? There were 3, yeah? 3 centimeters, if I'm not wrong. Yes. Yeah, so you can see. Now I also, in the part of view visualization, also on the DEM side, I'm using the resolution, theta resolution 8, and you can see the DEM particles, which are quite coarse. And if I use a 20 here, that's the same thing which also already explained for the STLs which are getting used on the coupling and which are getting saved. You see, they are just visualized quite nice. I'll go for 30 because I like it better. And I will go for the surface. So these are the particles. And as you can see, they are quite randomly positioned in this domain. And if I run the simulation, you can see they are falling down and settling in this. Oh, yes, it ran too far. Up to time 2. Oh, no, it's 40. Yes, up to times 2. So the particles are settling. And from time 2, our CFD-DEM simulation starts running and it starts floating the particles. So you can see now the particles are getting floated. But let's load also the CFD field side by side because it gets quite interesting if we can see that one also. As Hamid suggested and recommended, let's use the foam.foam file. Oh, we need to go for the decomposed case. And then let's create a slice in the middle. So that's the Y normal, yeah, no, Z normal, sorry. Don't show plane, don't triangulate it, and fly. Good. And so that's what I wanted to show. As you can see, this is our CFD field. Let me hide that one. The geometry can stay here. For the glide, it's fine. And let's color it with something different. So with velocity, because we might get a better understanding of what's happening there. So as you can see, the velocity or the fluid is coming in from the bottom with around, I think, 0.7. That's what we said. 0.6, 0.7 coming in. And then it goes around the particles. As you can see, in between the particles, the flow starts to speed up. So you can see in the gaps between the particles and the wall and in between the particles. And at some point, you can see this is the surface where the particle is touching this plane. The velocity is going quite close to 0 because we have a no slip on the surface. Hamid, you're muted.
Can you rotate it around y-axis to see the particle at the, yeah, this is the part.
And this is the dynamic mesh part of the story. As you can see, wherever we have particles, the mesh gets refined around it. And this is, so this was the original background mesh. So you see, this is the level 0. Then in the level 1, it breaks into 2 in each direction. And in level 2, it breaks to 4. So you can see that's how the mesh gets refined. And if I play this, you see, when as the particles are moving, this resolved mesh is also moving with them. So this refined mesh, better to say, is moving with them. And
I have a question here. What are these triangles doing here?
This is just, thanks, that's a very good one. This is just, what's the name? false representation in the para view. So they are not really triangles. So if I crinkle the slice, then you will see how does it look like. Basically, these are the cells. So when it caught the cells, there are some which are in between, and that looks like this. So they are not really triangles. But honestly speaking, I like the flat plane. Just, Hamid, is definitely true. Be aware that these lines are not really there. This is just, what's the right word for it? This is just visual misinterpretation.
Visualization, yeah, that's the way that Paravi visualizes this mesh structure.
Yeah, and then let's run it. If I run it slowly, you can see how the particles are running. And of course, on this plane, I can load different properties. Let's stop it. The pressure, so you can see how the pressure distribution looks like that. And if you look into a single particle below the particle, since we're coming to a stationary pressure, the pressure is higher. In the front, it's lower as expected. A very cool thing you can see is the separation or sort of separation points are on here. And yeah, you can see that's what resolve means. That means that the phenomena which is happening around the sphere is getting resolved using the simply the fundamental equations like the Navier-Stokes continuity, phase fraction equations, and solving them numerically. So you don't need any function.
And one point here is that this is just a demo simulation, not the actual simulation that is going to be validated against any experimental data. If you want to do that, you need to do more refinement on the simulation parameters to get validated results.
Yeah, thank you. That's also a very nice and valid disclaimer. So, but again, for your information, we are also working on that side. We are working hard on the validation of the code. And yeah, in soon future, there will be some dissemination also on this topic. And then cell level, you can see this is the refinement level of the cells. And what else? Yeah, void fraction. So you can see wherever we have a particle. So let me hide this slide. You can see we have a void fraction of 0, and outside it's 1. So that means that inside it's completely filled with solid, and outside it's with the fluid. And yes, with that one said, I think I covered most of the things that we wanted to do for today. And I hope that you enjoyed it. I hope that you learned new things. And I also hope at the same time that we could motivate you and convince you that the CFD, and especially the CFD-DEM, might be quite powerful tools for not just scientific, but also for industrial and engineering applications. But again, this is a point that I mention all the time. These are just tools, and you are the brains, engineers, scientists. So you need to make sure that these tools are doing the right job. So of course, we try to do our best to make the best tools, but to make to take the best results and the physical results out of them, you are responsible to put the right models, the right settings, and the right validation, calibration, whatever is required in there. Thank you very much, Hamid. Do we have any questions, or are there any points that you want to add?
No, we don't have any questions, and I just want to thank everyone for being with us during this lecture series. I hope this lecture series were useful for you, and hope we will see each other in soon future with other topics related to the CFD and DEM simulations. Thank you.
Great. Also, special thanks from my side to all of you for being with us, and it was a great pleasure. Hamid, thanks for also being with me and supporting also in this lecture. And yeah, as Hamid already said, looking forward to see you in the next lecture. Thanks, and take care. Bye.
Bye.